Okay, some properties of definite integrals. You just have to know all these. You have to be intimately familiar with all of these properties. The first one says the area under a single point is 0. If you've got some graph, f of x, and I want to find the area from A to A, there's no area under a single point. That's what this says. This one says, if you want to find the area from A to B, you would get the opposite answer as if you found the area. Okay, they wrote this in a weird way. I would have written this one A, B, and then negative B. It doesn't matter. This is the area from A to B. That's the opposite answer you would get if you flip these limits around and go backwards. When you're integrating this direction, you get a positive. When you go backwards, you get a negative. Flipping the limits around changes the sign. Look here, I've got B on the bottom, B on top. If you change these limits, all you got to do is put a negative in front of your integral. So in general, or more specifically, the integral from 1 to 2 of e to the x dx will be the opposite of the integral from 2 to 1, e to the x dx. Now, why would you ever look at something geometrically going backwards? You probably wouldn't. But when we learn later U substitution, there'll be times when we do a U sub and we'll end up with limits where we've got the bigger number on the bottom and it just looks weird. So what we'll do is we'll flip these around, and we're allowed to do that as long as we introduce a negative. Okay, this property here, these three together say that the definite integral is a linear operator, meaning you can distribute an integral over addition or subtraction, and you can pull a constant out. C here is just a constant that does not depend on x. This is very useful. And the reason we can do this is because the integral was defined in terms of limits, and limits are linear operators. We can distribute a limit over sums, differences, and we can pull constants out. Now, all of this, everything here, assumes that all of these integrals exist. If any of these, if this integral doesn't exist, then you weren't allowed to distribute it to begin with. We won't run into any of those cases in this class. And then this last one, this one should be pretty intuitive. This says you've got some graph here. Here's A, here's B, and say C is in between them. And I want to know the area, say, from A to B. What this says is the area under the graph from A to B is the same as just finding this area first, A to C, f of x, plus finding this area and then adding those together. I wrote that backwards. C to B. So this says you can start and stop integrals anytime you want. If I've got some integral over some region, I'm allowed to just pick a point in the middle, do a small integral, do another small integral, and add the answers together. But this value C here does not have to be in between A and B for this to be true. This is one of the weirdest things that happens with integrals. C does not have to live in between A and B. I could have a picture that looks like this. Here's A, here's B, here's C. Then this area, this integral, the integral from A to B, would be equal to this integral all the way here, plus, now this is, we got to think about this. This says from C to B, that's going backwards. In this picture right here, C, the bigger number, is on the bottom. So in this picture right here, we would want to think of that, like I was saying up there, as the opposite of B to C. I flipped the limits of integration and introduced a negative. That's always true. You're always allowed to do what I just did then. What I'm saying is, in this particular picture, this one would make more sense. Because what does this equation now say? This area equals the total area minus that chunk. So the point of all of this is this equation is always true no matter where A, B, and C live. C does not have to be between A and B like it does in this picture. This is always true. So this question says, we want to write the integral from -2 to 1 of -3x cubed plus 2x plus 2 dx as a sum of 3 integrals. There are literally an infinite number of ways I could do this. So I've got my interval, -2 to 1. I've got some function, it's some cubic. Maybe it looks like that, don't really care. This question is just saying, find some way to split it up into 3 regions. So I could do -2 to -1. Here's region number 1, dx, plus maybe -1 to 0. Call this region 2 here. Plus 0 to 1. This would be region 3 right here, from 0 to 1. That's one way I might split this up into 3 separate regions. Nobody said I had to do it that way. I could say the integral from -2 to 1 of f of x dx is the integral from -2 to 0 of f of x dx plus the integral from 0 to 4 f of x dx plus the integral. Now I got to go backwards. I got to undo. See, I went too far. I went all the way up to 4. Now I got to cut back all this. This would be the integral from 4 back to 1. See, because I put the bigger number on the bottom, this one's going backwards. Integrals are typically smaller, bigger. When you put the bigger number on the bottom, you're integrating backwards, which means this is really a negative. We're really subtracting off this area. So I did from -2 to 0. I did all this chunk. Then I went all the way up to 4. I went past where I wanted to go. And then I went, oh no, I went too far, and cut all this back out. Because remember, we could write this one here. I could switch these two, write that the other way, 1 to 4. But if I switch those, I have to put a minus in there. Now that would be weird. I don't know why we would ever want to go all the way to 4 and then go, oh, we went too far and chop a bunch back off. It's not like we would ever do that in practice. It's just understanding that we could. This is understanding that you're allowed to split up your region of integration into as many chunks as you want. And this is understanding that if you switch your limits, you can do that by just taking the opposite of whatever that definite integral was.